What if the closest star was hiding a planet? What if the closest star system to Earth was hiding a planet that only appears for a moment and then disappears again? Just 4 light years away, beyond the silent darkness between stars, lies a system that astronomers have studied for more than a century. It shines brightly in the southern sky. So bright, in fact, that anyone looking up from the southern hemisphere can see it without a telescope. That light belongs to Alpha Centauri. In cosmic terms, Alpha Centauri is practically our neighbor. The Milky Way galaxy stretches roughly 100,000 light-years across. Most stars we study lie tens, hundreds, or even thousands of light-years away. But Alpha Centauri sits just over 4 light-years from Earth. If the entire Milky Way were the size of North America, Alpha Centauri would not be across the continent, it would be on the same city block. For generations, scientists and dreamers alike imagined what might exist there. Because if humanity ever travels beyond our solar system, Alpha Centauri will almost certainly be the first destination. But there has always been one frustrating mystery. Despite being the closest star system to us, Alpha Centauri refused to reveal whether it had planets. This may sound strange. After all, astronomers have already discovered thousands of planets orbiting distant stars across our galaxy. Though some are enormous gas giants larger than Jupiter. Others are rocky worlds slightly bigger than Earth. Some systems are packed with tightly orbiting planets. Others stretch far outward into cold, dark space. Entire catalogs of alien worlds now exist. Yet for decades, the star system closest to Earth remained strangely silent. It was as if we could see mountains across an ocean, but not the hill just outside our own window. Part of the mystery lies in the nature of Alpha Centauri itself. Because Alpha Centauri is not just one star, it is a family. The system contains 2 sun-like stars known as Alpha Centauri A and Alpha Centauri B. These 2 stars orbit each other in a slow gravitational dance that takes about 80 years to complete. From far away, they appear almost like twins. Alpha Centauri A is especially similar to our Sun in size, brightness, and temperature. At first glance, this seems like good news for planet hunters. If planets formed around our Sun, perhaps they formed around Alpha Centauri A as well. Maybe rocky worlds orbit there. Maybe oceans exist beneath alien skies. Maybe entire planetary systems circle those distant suns. But the binary nature of Alpha Centauri complicates everything. Imagine trying to build a delicate sandcastle while 2 strong winds blow across the beach from different directions. That is roughly what happens in many binary star systems. When planets begin forming, they grow within a spinning disk of gas and dust surrounding a young star. Over time, tiny grains collide and stick together, gradually forming larger bodies. Eventually, those bodies can grow into planets. But when 2 stars orbit each other, their gravitational forces can stir that disk violently. The environment becomes chaotic. Instead of calm, stable growth, the building blocks of planets can be disrupted, scattered, or destroyed before they ever become worlds. For many years, theoretical models suggested that binary systems like Alpha Centauri might struggle to form planets at all. But even if planets did exist there, observing them would be incredibly difficult. Alpha Centauri is the 3rd brightest star visible in Earth's night sky. To poets and stargazers, that brilliance is beautiful. To astronomers searching for planets, it is a nightmare, because planets are faint, extremely faint. Compared to their host stars, planets shine billions of times dimmer. Trying to detect one is like attempting to spot a snowflake drifting across the face of a searchlight. The light from the star overwhelms everything nearby. Telescopes designed to detect tiny signals from planets must struggle against that blinding brightness. And brightness is only one part of the challenge. Alpha Centauri also moves. Yes, because it is so close to Earth, the star system appears to drift across the sky faster than almost any other star visible to the naked eye. This movement, called proper motion, means astronomers must track its position with extraordinary precision. A tiny error in calculations, an error smaller than the width of a human hair seen from kilometers away, can cause a telescope to miss its target completely. There is also the problem of perspective. Alpha Centauri lies within the dense plane of the Milky Way galaxy. The background behind it is crowded with distant stars and faint galaxies. If a tiny point of light appears near Alpha Centauri, how can scientists know whether it is actually a planet orbiting the star, or simply a faraway galaxy perfectly aligned along our line of sight? Distinguishing between those possibilities requires extremely careful analysis. Because of all these challenges, the search for planets around Alpha Centauri has been filled with excitement, hope, and disappointment. Several times in the past, astronomers believed they had finally found evidence of a planet. In 2012, scientists announced the possible discovery of an Earth-mass planet orbiting Alpha Centauri B. For a moment, it seemed like the breakthrough everyone had been waiting for. But as more data was analyzed, doubts emerged. The signal was incredibly subtle, buried deep within complex noise in the measurements. Eventually, many researchers concluded that the supposed planet was likely just an artifact created by tiny variations in the data. Another promising discovery faded away. And so, the mystery remained. For decades, astronomers kept searching. Meanwhile, discoveries elsewhere exploded. NASA's Kepler Space Telescope revealed something astonishing about our galaxy. Planets are not rare, they are everywhere. So statistical studies now suggest that most stars in the Milky Way probably host planets of their own. Some stars may have entire planetary systems far larger than ours. The galaxy could contain hundreds of billions of worlds. And yet, Alpha Centauri remained silent. That silence carried an emotional weight beyond science, because Alpha Centauri has long represented humanity's imagined first step into interstellar space. In countless science fiction stories, as explorers travel to Alpha Centauri to discover alien worlds, not because the system sounds exotic, but because it is close enough that such journeys are theoretically possible. Even with today's technology, a spacecraft traveling a small fraction of the speed of light could reach Alpha Centauri within a human lifetime. Future propulsion technologies, laser sails, nuclear drives, or fusion engines might reduce that journey even further. But what would explorers find when they arrived? A barren pair of stars? Or a system filled with planets? For many years, no one knew. Then a new telescope was launched. The most powerful infrared observatory ever built. A telescope designed to look farther into the universe than any instrument before it. The James Webb Space Telescope. Webb was not built to study nearby stars. Its mirrors and instruments were designed for something far more ambitious, to look deep into space and deep into time. Because when astronomers observe extremely distant galaxies, they are actually seeing light that left those galaxies billions of years ago. Webb's goal was to capture that ancient light. To study the first galaxies that formed after the universe itself was born. Everything about the telescope was optimized for faint signals, cold environments, distant objects, ancient photons stretched by cosmic expansion. But then a new idea began to emerge among scientists. What if Webb could do something unexpected? What if it could look at Alpha Centauri? At first, the idea sounded almost absurd. Pointing Webb directly at one of the brightest stars in the night sky would be like using night vision goggles to stare into a stadium spotlight. The detectors could be overwhelmed. The data could be ruined. In the worst case, the telescope itself could be damaged. But there was one reason scientists considered the attempt. Planets do not only reflect light, they also glow. Every planet absorbs energy from its star and releases some of that energy as heat. Even extremely cold worlds radiate faint infrared light. That light is invisible to human eyes. But Webb was designed specifically to detect infrared radiation. If a large planet orbited Alpha Centauri, Webb might not see the light reflected from its surface, but it might detect the planet's heat, a faint warmth shining beside a brilliant star, like a glowing ember next to a blazing lighthouse. And if Webb succeeded, it would accomplish something extraordinary. For the first time in history, humanity would directly search for planets orbiting the nearest sun-like star in the universe. The attempt itself marked a turning point. For generations, Alpha Centauri had symbolized proximity without knowledge, a bright lighthouse whose shoreline remained hidden. Now, for the first time, we had a telescope powerful enough to look directly into that blinding light. The question was no longer whether planets could exist there. The question was whether we could finally see them. And when the James Webb Space Telescope turned its golden mirrors toward that familiar star, something appeared in the data. Something faint. Something small. A tiny spark of infrared light, hiding beside the nearest sun-like star to Earth. But what scientists saw next would make the mystery even stranger, because the object they detected would soon vanish. The telescope that was never meant to look here. What if the most powerful telescope ever built was never meant to look at the closest star to Earth? The James Webb Space Telescope was designed for a very different mission. Its purpose was not to study nearby stars, and it was built to look farther than any telescope before it, farther into space, farther into time. Because in astronomy, distance is time. When we observe distant galaxies, we are not seeing them as they are today. We are seeing them as they were billions of years ago, when the universe itself was young. Light travels at a finite speed. Even moving at 300,000 kilometers per second, light still needs time to cross the immense distances between stars and galaxies. The light from Alpha Centauri takes just over 4 years to reach Earth. But the light from the most distant galaxies Webb observes began its journey more than 13 billion years ago. Those photons left their galaxies before Earth existed. Before the sun formed. Before our solar system was anything more than a cloud of gas drifting through space. That is the universe Webb was built to explore. The ancient universe. The faint universe. The cold and distant universe. And everything about Webb was engineered with that mission in mind. Its enormous golden mirror, made of 18 hexagonal segments, collects tiny amounts of faint infrared light. Its instruments are shielded behind a massive sunshade the size of a tennis court. That sunshade blocks heat from the sun, Earth, and Moon, allowing the telescope to cool to incredibly low temperatures, because infrared astronomy requires extreme cold. Any warmth from this telescope itself could drown out the delicate signals it tries to detect. Webb operates nearly 1 million miles away from Earth at a location called the second Lagrange point. There, gravitational forces from Earth and the Sun balance in a way that allows the telescope to orbit the Sun in perfect synchronization with our planet. From that distant position, Webb can stare deep into space for hours or even days without interference. It is one of the most sensitive astronomical instruments ever created. But that sensitivity comes with a limitation. Webb is designed to detect extremely faint light. Pointing such a sensitive telescope at something extremely bright is dangerous. And Alpha Centauri is extremely bright. To Webb's detectors, the light from Alpha Centauri could easily flood the sensors. Imagine trying to photograph a candle flame, using a camera designed to capture the faint glow of distant fireflies. The candle would overwhelm the image. The sensor would saturate. Important details would vanish in a storm of brightness. For this reason, telescopes like Webb rarely observed the brightest stars in the sky. But astronomers knew something important. Planets are not completely dark. They glow, not with visible light like stars, but with heat. When a planet absorbs energy from its star, it warms slightly. That warmth is radiated away as infrared light. Even a cold planet hundreds of degrees below freezing still emits a faint glow in infrared wavelengths. And Webb was designed precisely to detect infrared light. That meant a large planet orbiting Alpha Centauri might still be detectable, not by reflected starlight, but by its heat signature. A planet warmed by its star could shine faintly in infrared, like a stone that continues to release warmth long after sunset. But detecting that faint glow would require a special technique. Astronomers needed a way to block the overwhelming light from the star itself. The solution was something called a coronagraph. A coronagraph works like an artificial eclipse. Inside the telescope's instrument, a tiny mask blocks the central light from the star. By suppressing the star's brightness, the telescope can reveal faint objects nearby. The technique is similar to holding your thumb in front of the sun to block its glare so you can see something beside it. You cannot remove all the light, but you can reduce it enough to glimpse what lies nearby. Webb's mid-infrared instrument, known as MIRI, contains several coronagraphs designed for exactly this purpose. MIRI operates at wavelengths where cooler objects shine most strongly. At around 15 micrometers, and a planet with temperatures between 200 and 300 Kelvin, similar to many objects in our outer solar system, can produce detectable infrared radiation. If a gas giant similar to Saturn orbited Alpha Centauri, MIRI might be able to see it. But there were still enormous technical challenges. The first problem was alignment. Coronagraphs require extremely precise positioning. The star must be placed exactly behind the mask. If the alignment is even slightly off, the light leaks around the edges and floods the image with glare. Normally, telescopes simply point directly at their target star. But Alpha Centauri was too bright for Webb's normal acquisition process. Pointing directly at it could overwhelm the sensors before the coronagraph even had time to block the light. So, astronomers developed a different strategy. Instead of pointing directly at Alpha Centauri, Webb would first lock onto a nearby reference star that was much dimmer. Once the telescope stabilized and its orientation was perfectly calibrated, it would perform a carefully calculated maneuver known as a blind offset. This maneuver shifted the telescope's aim by a precise amount, placing Alpha Centauri directly behind the coronagraph mask. The entire move had to be calculated in advance with incredible precision. Because Alpha Centauri is so close, its position in the sky changes slightly throughout the year due to a phenomenon called parallax. As Earth orbits the Sun, nearby stars appear to shift position slightly relative to the distant background of space. This shift is tiny. But for a telescope as precise as Webb, even tiny shifts matter. Scientists had to calculate the exact position Alpha Centauri would occupy at the precise moment of observation. They also had to account for the system's proper motion. Alpha Centauri drifts across the sky faster than most stars because of its proximity to Earth. And then there was the binary companion, Alpha Centauri A does not shine alone. Its partner, Alpha Centauri B orbits nearby. Even if the coronagraph perfectly blocked the light from Alpha Centauri A, the second star could still scatter light across the detector. That scattered light could create complex diffraction patterns, bright spikes and halos that might hide or mimic faint objects. This meant the data processing would be extremely difficult. Astronomers would need to model how light from both stars behaved inside the instrument. They would need to subtract those patterns from the images, leaving behind only real astronomical signals. Before the observation ever happened, scientists ran months of simulations. They modeled the telescope. They modeled the stars. They modeled how light would scatter and bend inside the instrument. They tested the blind offset technique again and again in software. And because once the real observation began, there would be no room for mistakes. The James Webb Space Telescope is one of the most valuable scientific instruments ever built. Its observing time is precious. Every hour must be carefully planned, and pointing Webb toward one of the brightest stars in the sky was a risk. But the potential reward was extraordinary. If Webb succeeded, it would accomplish something no telescope had ever done before. It would directly probe the region around the nearest sun-like star in the universe, searching for planets. For decades, Alpha Centauri had been a mystery, a bright neighbor whose planetary system, if it existed, remained invisible. Now humanity had a tool powerful enough to finally look into that blinding light. When the observing campaign began in August 2024, Webb stared at Alpha Centauri for hours. Now, long exposures collected faint infrared photons drifting across interstellar space. Each photon had traveled more than 4 years to reach the telescope. They arrived one by one, quietly striking Webb's detectors. Those tiny signals were converted into numbers. The numbers were transmitted across space, back to Earth. When scientists first saw the raw data, it looked chaotic. Diffraction spikes radiated outward from the masked star. Residual glare filled parts of the image. Light from Alpha Centauri B created streaks across the field of view. Detector artifacts appeared as strange patterns of brightness. To an untrained eye, the images looked almost meaningless, but hidden inside that chaos was information. And as astronomers began carefully processing the data, something unexpected began to appear. A faint signal, a tiny point of warmth, and a dot of infrared light sitting just beyond the brightest region of starlight suppression. At first, no one celebrated, because Alpha Centauri had fooled scientists before. Signals had appeared in the past, only to disappear under closer scrutiny. But this signal was different. It was stable, consistent, and exactly where a planet might exist. The object was small, extremely faint, nearly 10,000 times dimmer than the star beside it. But in astronomy, that was enough. For the first time in history, Webb may have glimpsed something beside the nearest sun-like star to Earth. A tiny spark of infrared light. A possible world orbiting Alpha Centauri. But before anyone could call it a planet, the scientists had to ask the most important question in astronomy. Was it real? Or was it something else entirely? And as they began analyzing the signal more carefully, the mystery only deepened. Because the object would soon receive a simple name, S1, Source 1, and what happened next would turn a possible discovery into one of the strangest puzzles in modern astronomy. The dot that shouldn't exist. What if, hidden inside a storm of starlight, there was a planet waiting to be seen? When the first data from the James Webb Space Telescope arrived on Earth, the images did not look promising. At first glance, they looked chaotic. Bright diffraction spikes stretched outward from the masked star like glowing blades. Rings of scattered light curled around the center of the frame. Faint streaks crossed the image where light from Alpha Centauri B had spilled into the detector. The entire field looked like a storm of brightness and shadows. Nothing about it resembled the clean, beautiful images people often see in space documentaries. But astronomers are used to this. Raw telescope data almost always looks messy. Before any discovery can be made, scientists must peel away layers of interference, instrument noise, optical artifacts, background light, cosmic radiation strikes. All of it must be removed, and that process can take weeks, sometimes months. To begin the analysis, Researchers first needed to understand how Webb's instruments behave when no planets are present. They observed reference stars under nearly identical conditions. Stars with similar brightness, observed using the same coronagraph and instrument settings. These reference images acted like fingerprints of the telescope itself. They showed how light naturally scatters inside the instrument, where diffraction patterns appear, where noise tends to form. Once those patterns were understood, astronomers could subtract them from the Alpha Centauri images. This technique is known as reference star differential imaging. It is one of the most powerful tools astronomers use when searching for extremely faint objects near bright stars. Layer by layer, the unwanted patterns began to disappear. First, the large diffraction spikes were modeled and removed. Then, residual glare from the star was reduced. Next came a mathematical technique known as principal component analysis. This method analyzes patterns of noise across many images and identifies structures that consistently appear due to the instrument rather than real objects. Those patterns are removed as well. Each step was like clearing fog from a window. At first, the view was murky. Then shapes began to emerge. Then details. Then, slowly, something unexpected appeared. A small point of light. At first, it was barely visible. Just a faint glow sitting slightly away from the center of the image. But as more noise was removed, the point remained. It did not disappear. It did not move randomly like detector noise. It stayed in the same position, stable, distinct, and clearly separated from the star. The signal was located about 1.5 arcseconds away from Alpha Centauri A. That may sound incredibly small, and it is. An arcsecond is a unit astronomers use to measure tiny angles in the sky. There are 3,600 arcseconds in a single degree. To understand just how small that is, imagine standing in New York City and looking toward Los Angeles. An arcsecond would correspond to the width of a coin seen from thousands of kilometers away. Yet Webb's instruments are precise enough to detect objects separated by such tiny angles. At Alpha Centauri's distance, and that separation translates to something remarkable. Roughly 2 astronomical units. An astronomical unit is the distance between Earth and the Sun. So the faint object appeared to be orbiting Alpha Centauri A at about twice the Earth-Sun distance, right near the outer edge of the star's habitable zone, the region where temperatures could allow liquid water to exist on a rocky planet's surface. But this object was probably not a rocky world. Based on its infrared brightness, scientists could estimate its temperature. The signal corresponded to a temperature somewhere between 200 and 250 Kelvin. That is roughly minus 50 degrees Celsius. Cold by human standards, but not unusual for planets in the outer regions of solar systems. The brightness also suggested something about the object's size. Small rocky planets are extremely difficult to detect through direct imaging. They simply do not emit enough heat. But gas giants are different. Large planets made mostly of hydrogen and helium can radiate significantly more infrared light. The data suggested something roughly comparable in mass to Saturn, a mature gas giant quietly orbiting its star. Not a blazing hot Jupiter hugging the surface of its sun. Not a glowing newborn planet still radiating heat from its formation. But an old, cooled world. A planet that may have been orbiting Alpha Centauri for billions of years. And if that interpretation was correct, the discovery would be historic. Because direct imaging of exoplanets usually favors young systems. Young planets still glow brightly from leftover formation heat. They are easier to see. Older planets are cooler, dimmer, harder to detect. Yet this object appeared to be exactly that, a mature world orbiting a sun-like star in the nearest stellar system to Earth. And that alone would be extraordinary. But before anyone could celebrate, The scientists had to do something difficult. They had to try to destroy their own discovery. In science, every new signal must survive intense skepticism. Extraordinary claims require extraordinary evidence. And the team knew that Alpha Centauri had fooled astronomers before. So they began testing every alternative explanation. First, they considered the possibility that the object was not a planet at all. It could be a distant galaxy. At the background behind Alpha Centauri lies within the crowded plain of the Milky Way. Faint galaxies sometimes appear as tiny unresolved points of infrared light. If one happened to align perfectly behind Alpha Centauri, it might appear exactly where this signal was detected. To test this idea, astronomers searched through deep sky catalogs. They examined archival images from other telescopes. They checked whether any known galaxies occupied that location. None did. No previously recorded object matched the signal's position. Next, they considered a closer possibility. Perhaps the object was not far away, but very close. An asteroid. Small bodies within our own solar system occasionally drift through telescope observations. If an asteroid passed through the field of view during the observation, it might appear briefly as a faint point of light. But asteroids move. Even over the course of a few hours, their motion across the sky becomes noticeable. Scientists examined the individual exposures taken by Webb. If the signal belonged to an asteroid, its position should shift slightly from frame to frame, but it did not. The point remained fixed relative to Alpha Centauri, exactly where a planet should be. Then came the most frustrating possibility: instrument artifacts. Coronagraphs are complex optical systems. Under certain conditions, tiny speckles of residual starlight can appear in images. These speckles sometimes mimic the appearance of faint planets. To test this, researchers performed a clever experiment. They inserted artificial planets into the raw data, simulated signals with known brightness and position. Then they processed the images using the same analysis pipeline. Real planetary signals behave in subtle but predictable ways. They maintain specific statistical properties as noise is removed. Artifacts behave differently. When scientists compared the behavior of the detected signal with the simulated planets, the match was striking. The signal behaved exactly like a real astronomical object. By this point, the team had ruled out most alternative explanations. The detection reached a statistical significance strong enough to rule out random noise with extremely high confidence. In the language of science, it approached what researchers call a 5 sigma detection. The probability that it was merely a fluctuation in the detector was vanishingly small. Something real had left its mark in the data. Still, caution remained. Because a single observation is never enough to confirm a planet. Planets move. They orbit their stars according to the laws of gravity. And that motion provides the ultimate proof. If the object truly orbited Alpha Centauri A, its position would shift slightly over time. Weeks or months later, the telescope should see it again, in a slightly different location, tracing the arc of an orbit. But if the object failed to appear again, the interpretation would have to be reconsidered. For now, the researchers gave the mysterious signal a simple name: S1. Not planet, not world, just Source 1, a faint infrared object located near Alpha Centauri A, the closest star system to Earth, at roughly 2 astronomical units from its star, possibly a gas giant. Possibly the closest directly imaged exoplanet candidate ever detected. The discovery was exciting, but it was only the beginning, because the real test would come next. Follow-up observations were scheduled for early 2025. If S1 appeared again where orbital mechanics predicted, the case for a real planet would become incredibly strong. But if it did not, then something far stranger might be happening. Because planets can orbit, planets can cool, planets can hide behind starlight. But there is one thing planets are not supposed to do. They are not supposed to vanish. And yet, that is exactly what would happen next. The planet that vanished. What if the closest planet ever discovered suddenly disappeared? When the James Webb Space Telescope first detected the faint signal known as S1, the discovery sparked cautious excitement among astronomers. The data had passed every internal test. The signal remained stable through multiple processing methods. It matched the statistical behavior expected from a real astronomical object. But science demands more than one observation. To confirm that S1 was truly a planet orbiting Alpha Centauri A, scientists needed to see it again. And more importantly, they needed to see it move. Planets do not stay frozen in space. They orbit their stars according to the laws of gravity first described by Johannes Kepler more than 4 centuries ago. As a planet travels along its orbit, its position relative to the star slowly changes. Sometimes the shift is tiny. Sometimes it is dramatic. But motion is inevitable. If S1 were truly a planet, then months later it should appear again in Webb's observations, slightly displaced from its original position. That movement would trace the arc of an orbit. It would transform a mysterious signal into a confirmed world. So follow-up observations were scheduled. The first opportunity arrived in February 2025. By that time, several months had passed since the original August 2024 detection. That should have been enough time for a planet orbiting at roughly 2 astronomical units to shift slightly along its path. Astronomers predicted where S1 should appear. Using the original detection, and they simulated thousands of possible orbital paths. Some orbits would be nearly circular. Others could be elongated ellipses. Some might be tilted relative to our line of sight. But almost all of those possibilities placed the planet somewhere within Webb's detectable field of view. When the telescope turned again toward Alpha Centauri A, anticipation was high. The observing procedure had already been tested. The blind offset technique worked. The coronagraph aligned perfectly. The data processing pipeline had proven capable of extracting faint signals from overwhelming starlight. If S1 was real, Webb should see it again. Hours of observation began. Infrared photons once again streamed into the telescope's detectors. The raw images arrived, and at first, everything looked familiar. The same diffraction spikes, the same residual glare, the same chaotic storm of light surrounding the massed star. Scientists ran the same processing pipeline used during the original discovery. Reference star subtraction, noise modeling, principal component analysis. They focused on the predicted region where S1 should appear. Nothing. No faint dot, no trace of warmth, just empty space. At first, the team assumed the planet might have moved farther than expected. Orbital mechanics allows for a wide range of possible trajectories, and depending on the shape and orientation of its orbit, the planet might have shifted to a slightly different angle. So, the researchers widened the search area. They examined the entire field of view. Still nothing. S1 was gone. Perhaps something had gone wrong with the analysis. Maybe the processing pipeline had suppressed the signal accidentally. So the data were reprocessed. Again and again. Different parameters were tested. Different noise thresholds were applied. Independent teams analyzed the images separately to avoid confirmation bias. The result remained the same. S1 did not appear. At this point, the simplest explanation seemed unavoidable. Maybe the original detection had been an illusion. Even a 5 sigma detection does not guarantee truth. Rare statistical fluctuations can occur. Instrument artifacts sometimes survive multiple tests before revealing themselves as false signals. The history of astronomy contains many such examples. Signals once celebrated as discoveries later faded into noise. Perhaps S1 was simply another case like that, but something about the August detection resisted this conclusion. The signal had behaved too consistently, It appeared in multiple subsets of the data. It matched the expected profile of a real point source, and its brightness corresponded closely with theoretical predictions for a gas giant at that distance. Still, without a second detection, the case remained uncertain. Then, April 2025 arrived. Another opportunity to observe Alpha Centauri. Perhaps February had simply caught the planet at an unfortunate moment in its orbit. Maybe it had moved closer to the star, where residual glare from the coronagraph made it difficult to detect. A few more months might allow it to swing outward again. When the April observations were completed, the analysis began once more. The same careful procedures, the same data processing, the same search for the faint signal. But once again, nothing. S1 had vanished. There is a special kind of silence that follows a result like this. Not the silence of failure, the silence of confusion. Because the telescope had worked perfectly, the sensitivity of the observations matched, or even exceeded, the original detection. If a Saturn mass planet were sitting where many models predicted, Webb should have seen it, yet the images showed only darkness. For a brief moment, the possibility that S1 had never existed seemed almost unavoidable. But then scientists began looking at the problem from a different angle. Not through the telescope, but through geometry. Coronagraphs do not see space equally in every direction. Their sensitivity varies depending on position. Light bends around the edges of the mask through a process known as diffraction. Some regions near the star are easier to observe. Others are dominated by residual glare. Imagine shining a flashlight through a narrow opening. The beam would not be perfectly uniform. There would be brighter arcs, darker gaps, tiny blind spots where objects could disappear. A faint object drifting through that beam might appear bright in one position and invisible in another, even though the object itself never changed. If S1 followed a highly eccentric orbit, that its distance from Alpha Centauri A could vary dramatically. At the farthest point in its orbit, called apastron, it would be far from the star. That separation would place it in the coronagraph's most sensitive region, exactly where Webb detected it in August 2024. But as the planet moved along its orbit toward periastron, the closest point to its star, it would drift into areas dominated by residual starlight. In those regions, the planet's faint infrared glow could easily be overwhelmed. The planet would still exist. Webb simply would not be able to see it. To test this idea, astronomers began running orbital simulations. Thousands of possible orbits were generated, then tens of thousands, eventually millions. Each simulation started with the original August detection. Then scientists asked a simple question. How many of those possible orbits would produce exactly the pattern observed? Visible in August 2024, but hidden in February and April 2025? The answer was surprising. More than half of the simulated orbits produced that exact behavior. In many plausible scenarios, S1 would have been near the farthest point of its orbit during the August observation. That position would place it at maximum separation from the star, perfect for detection. But only a few months later, the planet would begin moving inward along its elliptical path, crossing into regions where Webb's coronagraph simply could not see it. The planet would not disappear. It would merely become invisible again. This realization changed everything. Because now the non-detections in 2025 did not weaken the planet hypothesis. In many cases, they actually supported it. The mystery deepened even further when scientists revisited an older observation. In 2019, several years before Webb launched, astronomers using the Very Large Telescope in Chile reported a faint signal near Alpha Centauri A. That candidate was labeled C1. At the time, the detection was considered tentative. Ground-based telescopes must observe through Earth's turbulent atmosphere. Distortions in the air can create false signals that mimic planets. So, the C1 candidate was never confirmed. But when researchers compared the position of C1 with the possible orbits of S1, something remarkable appeared. A single planet following an eccentric orbit could explain both signals: the object seen near the star in 2019, the object seen farther away in 2024, and its disappearance in 2025. All of them could belong to the same world. If that interpretation is correct, the planet's orbit may be unusually stretched, an eccentricity near 0.4, far more elongated than Earth's nearly circular path around the Sun. The orbital period might be between 2 and 3 Earth years. Such an orbit would make S1 unlike any major planet in our solar system, and it would perfectly explain its strange vanishing act. Sometimes visible, sometimes hidden. A traveler moving through regions of space where even the most powerful telescope ever built cannot always see it. If that is true, then the story of S1 is far from over. Because orbital simulations suggest that sometime in 2026, the planet may swing outward again, back into Webb's field of view. And if it appears exactly where gravity predicts, then the closest star system to Earth may already contain a giant planet, waiting quietly, just 4 light-years away. A giant world, next door. What if the closest star system to Earth already contains a giant planet, quietly orbiting just 4 light-years away? If the mysterious signal known as S1 truly represents a planet, it would immediately become one of the most fascinating worlds ever detected. Not because it is the largest, not because it is the hottest, but because of where it exists. Alpha Centauri A is the closest sun-like star to Earth. And S1, if confirmed, would orbit right inside that nearby stellar neighborhood. The infrared light detected by the James Webb Space Telescope provides the first clues about what this world might be like. At roughly 15 micrometers in wavelength, the object radiated heat consistent with a temperature between about 220 and 250 Kelvin. That translates to roughly minus 50 degrees Celsius. Cold by human standards. Colder than Antarctica during the deepest winter, but far warmer than the cloud tops of Saturn. This temperature suggests something important. S1 is not a scorching hot Jupiter hugging its star. It is not a young planet still glowing with leftover heat from its formation. Instead, it appears to be something quieter, older, cooler, a mature gas giant. Based on the brightness of its infrared emission, scientists estimate that S1 could have a mass somewhere near Saturn's, perhaps between 80 and 150 times the mass of Earth, large enough to gather a thick envelope of hydrogen and helium, but not large enough to ignite nuclear fusion like a star. In other words, if S1 is real, it would be a true planet, and a massive world slowly orbiting a star remarkably similar to our own Sun. And its orbit may place it in a surprisingly interesting location. Alpha Centauri A is slightly brighter than the Sun. That means its habitable zone, the region where temperatures could allow liquid water on a rocky planet's surface, lies a bit farther away from the star than Earth's orbit lies from ours. Based on the observations, S1 appears to orbit somewhere between roughly 1 and 2 astronomical units from Alpha Centauri A. That distance places it near the outer edge of the star's habitable zone. Of course, a gas giant itself would not be habitable. Gas giants do not have solid surfaces. What appears to be the surface of such planets is simply the upper layer of their atmosphere. Beneath the clouds, pressure increases rapidly. Gases compress into exotic states of matter. Temperatures rise. Eventually, the atmosphere becomes so dense that hydrogen begins behaving like a liquid metal. There are no continents, no oceans, no ground where life as we know it could stand. But giant planets rarely travel alone. In our own solar system, Jupiter has more than 90 moons. Saturn has even more. Some of those moons are tiny, irregular rocks captured by gravity. But others are worlds in their own right. Consider Titan, Saturn's largest moon. Titan has a thick atmosphere made mostly of nitrogen. Rivers and lakes flow across its surface, not with water, but with liquid methane and ethane. Then there is Europa, one of Jupiter's moons. Europa's icy crust hides a vast ocean beneath its frozen surface. That ocean may contain more water than all of Earth's oceans combined. And Enceladus, another moon of Saturn, ejects enormous plumes of water vapor into space. Inside those plumes, scientists have detected organic molecules and chemical energy sources that could potentially support life. These moons are not barren rocks. They are complex environments. Now imagine a similar moon orbiting S1. But instead of receiving faint sunlight from a distant star like Jupiter or Saturn, it would orbit inside the habitable zone of a sun-like star. Such a moon could receive far more energy from its star. If it had a thick enough atmosphere, surface temperatures might allow liquid water to exist openly. Oceans might flow across its surface. Clouds could form. Rain could fall. The moon might experience seasons driven by the orbit of its giant host planet, and the sky above that alien world would be unlike anything on Earth. Because Alpha Centauri is not a single star, it is a binary system. While Alpha Centauri A shines brightly overhead, its companion star, Alpha Centauri B, would also be visible. Sometimes faint, sometimes brighter, depending on its position in the 80-year orbit around its partner. Over decades, the second sun would slowly shift across the sky, casting subtle secondary shadows, creating long-term cycles of changing light. It would be a sky with two suns, a sky that no human has ever seen in person. The possible orbit of S1 adds another layer of complexity. Based on current simulations, the planet may follow an eccentric orbit. Instead of tracing a nearly circular path like Earth, its orbit could stretch into a long ellipse, with an eccentricity near 0.4. That means the planet's distance from Alpha Centauri A would change dramatically over the course of each orbit. At its closest approach to the star, S1 would receive significantly more radiation. At its farthest point, the energy reaching it would drop considerably. If S1 hosts large moons, those moons might experience dramatic climate variations. During one part of the orbit, temperatures might rise, ice caps might melt, oceans might expand. Later, as the planet moves farther from its star, temperatures could fall again. Ice might return. Climate cycles could stretch across years instead of seasons. We have never observed such a system directly before. All exoplanets imaged through direct observation so far have been young and extremely distant from their stars. Those planets glow brightly because they are still hot from formation. But they tell us very little about mature planetary systems like our own. S1 would be different. If confirmed, it could become the first directly imaged example of a billion-year-old gas giant orbiting within the temperate region of a sun-like star. In many ways, it would resemble a distant mirror of our own solar system, a giant planet similar in mass to Saturn, orbiting a sun-like star, possibly surrounded by moons and located just beyond our cosmic doorstep. The discovery would also reshape our understanding of planetary formation. For decades, astronomers debated whether planets could easily form in binary star systems like Alpha Centauri. The gravitational influence of a nearby companion star can disturb the disk of gas and dust where planets form. Some models suggested such environments might prevent stable planets from developing. Yet if S1 truly exists exactly where Webb detected it, then planets clearly can form there. Stable orbits are possible. Worlds can survive even within complex multi-star environments. And that realization carries enormous implications, because binary star systems are not rare. They are incredibly common. Roughly half of all stars in our galaxy belong to binary or multi-star systems. If planets can form and survive in systems like Alpha Centauri, then the number of potentially habitable worlds in the Milky Way may be far larger than scientists once imagined. Entire populations of planets may exist in places we previously overlooked, hidden in the gravitational dances of binary stars. And somewhere among those countless worlds, some may resemble Earth. For now, S1 remains only a candidate, a faint signal, a possible world glimpsed briefly through the glare of a nearby star. But if future observations confirm its existence, then the nearest sun-like star to Earth may already host a giant planet, and possibly an entire system of moons, worlds that have quietly circled their star for billions of years, just 4 light-years away, closer than any other planetary system humanity has ever glimpsed. And yet, we have only just begun to notice it. The next time we look, what if the closest planet to Earth is already there, waiting for the right moment to appear again? For now, the mysterious signal known as S1 remains unconfirmed. It appeared once, clear enough to capture the attention of astronomers around the world, bright enough to pass the statistical tests that normally separate real discoveries from noise. But then, it vanished. The February 2025 observations could not see it. Neither could the follow-up observations in April. To an outside observer, that might sound like the end of the story, a false signal. Another illusion created by instruments pushing the limits of what they can detect. But astronomy rarely works that way, because the universe often reveals itself slowly, piece by piece. And sometimes the most important discoveries arrive not in a single dramatic moment, but through patience. When scientists began running detailed orbital simulations of S1, something remarkable emerged. If the object truly follows an elongated orbit around Alpha Centauri A, then its strange behavior makes sense. In August 2024, when Webb first detected the faint infrared signal, the planet may have been near the farthest point of its orbit, the place astronomers call a pastron. At that distance, the separation between the planet and the star would be greatest. And that is exactly where telescopes like Webb are most sensitive. The coronagraph suppresses the star's light most effectively at certain distances from the center. If S1 happened to pass through that region at the right time, Webb could briefly see it. But as the planet continued along its orbit, gravity would pull it gradually closer to its star, toward periastron, the closest point of its orbit. And as it moved inward, the planet would drift into regions where the coronagraph becomes less effective. Residual starlight would dominate the image. The faint glow of the planet would become buried beneath the glare. From Webb's perspective, the planet would simply disappear, not because it was gone, but because it had slipped into a blind spot. Orbital simulations suggest that this scenario is not just possible. It may actually be likely. In fact, a large fraction of stable orbital solutions predict exactly the pattern that astronomers observed, visible in August 2024, invisible during the observations of early 2025, hidden, but still there. If those simulations are correct, then S1 may follow an orbit that takes between 2 and 3 Earth years to complete. That means the planet continues its silent journey around Alpha Centauri A even now. Somewhere along that path, the geometry will change again. The planet will slowly move outward, away from the star's blinding glare, back toward the region where Webb can see it. According to current models, that moment could arrive sometime in 2026. When that window opens, astronomers will have another opportunity. Another chance to look toward Alpha Centauri. Another chance to test whether S1 is truly a planet. Nay, if Webb observes the system again and finds the faint infrared signal exactly where orbital mechanics predicts, the evidence will become overwhelming. Because random noise does not follow predictable orbits, instrument artifacts do not move according to the laws of gravity. But planets do. And if S1 appears again in the expected position, tracing the arc of a stable orbit, then humanity will have discovered something extraordinary. The closest directly imaged exoplanet candidate ever detected. A giant world orbiting the nearest sun-like star to Earth. A planet quietly circling its star just 4 light-years away. But there is another possibility. If Webb observes Alpha Centauri again in 2026 and finds nothing, no faint glow, no infrared signal, no trace of S1 anywhere along the predicted orbit, then the mystery deepens. Because the original detection was strong, stronger than many early discoveries that later became confirmed planets, if the signal cannot be explained by orbital motion, then astronomers will have to consider other possibilities. Perhaps something unusual happened in the instrument. Perhaps an unknown astrophysical phenomenon produced a temporary signal. Or perhaps something even stranger occurred. Science has encountered such puzzles before. Moments where observations challenge expectations. Where nature behaves in ways we do not yet fully understand. Sometimes those puzzles disappear with more data. Sometimes they reveal entirely new physics. For now, the universe has left us with a question. Somewhere within the bright glare of Alpha Centauri, something produced a faint spark of infrared light. Something real enough to pass rigorous statistical tests. Something positioned exactly where a planet might exist, but something that has not yet revealed its full story. The truth may already be orbiting that distant star, moving silently along an invisible path, and waiting for the moment when the geometry of space once again allows us to see it. There is something deeply poetic about this possibility. For thousands of years, humans looked up at the night sky without knowing that other planets existed around distant stars. The idea of exoplanets was once pure speculation. Today, we know that our galaxy is filled with them. Thousands have already been discovered. Billions more likely exist. And yet the system closest to us, the one star system that could someday become humanity's first interstellar destination, remains partially hidden. Alpha Centauri shines brightly above us, close enough that its light reaches Earth in just over 4 years. Close enough that future spacecraft may one day travel there. But its worlds, if they exist, are still emerging slowly from the glare of their star. Perhaps in 2026 we will see S1 again. Perhaps the faint infrared glow will reappear exactly where gravity predicts. And if it does, then somewhere around Alpha Centauri A, a giant planet has been orbiting quietly for billions of years, long before humans built telescopes, long before life even appeared on Earth. A world that has completed countless journeys around its star, while our species was still learning to look at the sky. For now, we can only wait. The photons leaving Alpha Centauri today will arrive at Earth 4 years from now, and somewhere within that light may be the next clue. Because sometimes the universe does not reveal its secrets all at once. Sometimes it lets us glimpse them only briefly. A faint spark beside a brilliant star, a whisper hidden in the glare, a world that appears, disappears, and waits patiently for us to notice it again.